I welcome you in this lecture on open and closed loop systems. In the previous lecture, we discussed open and closed loop control systems with simplistic block diagram. Representations. So in today's lecture, we'll discuss general block diagram. We'll discuss the general block diagram representation of both open and closed loop systems. Open and closed loop control systems. With examples, of course. Now, in the previous lecture, what I said was that an open loop control system can be represented as we have a controller, and then we have a process or plant, output, and an input, sometimes also called as reference input or reference level. So today we'll dig a bit deeper into the block diagrams. So the general form of this is the simplistic block diagram. Of an open loop control system. Now we'll draw the general block diagram of a control system, which would look like we have an input, then a transducer, an input transducer, then a controller, then a summing junction, then we'll be having a process or plant. Let me use a different marker. Process or plant. This is basically a summing junction here, and we have a controller there. Then after this we'll be again having a summing junction. So these summing junctions are for the fact that we can have any disturbance. I'll write here disturbance. Any disturbance can arrive or enter our system. So we represent it as disturbance 1, and some disturbance can even enter at the output stage. So we represent it as disturbance 2, and this is the final output. Now let's try to understand this block diagram by the example of an elevator. As we have already discussed the example of an elevator, that say for example we are inside a tall building and we want to go up from, say for example, from ground floor to 1, 2, 3rd, 5th floor. So what happens is that once we enter the elevator, we push the button 5. So as I said, the push to the button would be the input. Push to the button is the input. So when we press button 5, what happens is that the input transducer converts this push to an electrical signal, because our controller may not be able to understand the physical push. So the input transducer, which can be, say for example, a potentiometer, which converts this push to some voltage signal or voltage level, and that voltage signal is being fed to the controller, and that controller then feeds that signal to our process plant. The processor plant in this case can be, for example, a motor, the belts that are used for moving the elevator up, and it can include even the physical structure of the elevator. So your process of plant consists of a motor, belt, physical system of the elevator, and plus the electrical network or the electrical equipments that are used in its construction. The controller, as I said, receives a voltage level. The controller, for example, can be a microcontroller. Again, a microcontroller is an electrical device. It will understand everything in terms of voltages. So that's why we need an input transducer to convert the physical push to an electrical signal, which is being then fed to a controller. The controller controls the electrical machinery like the motor, the belt, etc., so that it eventually moves up. Now say for example we push button 3. So corresponding to push 3, we have to reach the third story of the building. Corresponding, if we push button 4, we need to reach the fourth floor of the building. So what happens basically is that this push 3 gets converted to some voltage. Say for the sake of saying, it gets converted into 3 volt signal. So when the controller receives a 3 volt signal, for example, it tells the process or the plant or the motor to move the lift or the elevator to the third story. Likewise, if we push the button 4, it generates some voltage level, say for example 4 volts. When the controller receives this 4 volt signal, it tells the motor to move to the fourth floor, or it pushes the circuitry such that the lift has to reach to the fourth floor. Now in this case, we have in between the controller and process, we see a summing junction, which represents the output of the controller and some disturbance here. Let me draw it here again. So we have a controller here, and then a summing point or a summing junction, and then the process. A controller. Ideally, the output of the controller should reach to the processor, to the process or the plant. But sometimes what happens, disturbances also enter our system. These disturbances are unavoidable. A disturbance, for example, in this case can be a voltage fluctuation. Can be a voltage fluctuation. A disturbance, as I said, can be a voltage fluctuation. For example, sunlight entering an air-conditioned room can be treated as a disturbance for that system. Now, say another example. Say, for example, we have an antenna positioning system wherein we try to rotate an antenna by some angle. Say, for example, we intend to rotate an antenna by some angle, say, for example, 30 degrees. So what happens is that wind may come at the same time, and it may blow or move the antenna by another 20 degrees or 5 degrees. So the wind in an antenna positioning system is treated as a disturbance. Likewise, sunlight in an air-conditioned room can be treated as a disturbance, and these disturbances are all unavoidable. So these disturbance signals, they represent inputs which affect the control system's output and result in increase of system error. Error would be the deviation from the exact value. Say for example, we want to maintain the room temperature at, say for example, 20 degrees centigrade, but when sunlight enters the room, the temperature may rise. So the more it rises, say for example, if it reaches to 25 degrees centigrade, the error in this case would be 5 degrees centigrade. So this disturbance eventually results in creating an error. So it is basically the job of a control system engineer to properly design the control system to partially eliminate the effects of disturbances. So in a nutshell, under the influence of under the influence of disturbances, the output may not be the same as is desired. So in open loop systems, the error caused by disturbances cannot be reduced or minimized. So as to avoid the effect of disturbances, so in order to avoid the effect of these disturbances, what we do is that we use closed loop control systems. So the problem of open loop systems is being tackled by closed loop control systems. Now let's again take a generalized form of block diagram of a closed loop system. So we have an input transducer, then we have a summing junction, then of course a controller, and then again a summing junction, and then we have processor plant, and then again a summing junction, and then the output. This is, let me use a different color. So we have input transducer here, we have a summing junction to which some noise or disturbance gets added, and then we have a controller, again a summing junction to which some disturbance gets added, and then we have the processor plant, and then we have disturbance, again disturbance 2, disturbance 1. This is basically a summing junction. Let me erase it. Now this is a, since it has to be a closed loop control system, so there has to be a feedback from the output side to the input side. So this is the feedback loop, as we have already discussed it in the previous lecture. This is a transducer, but this time it's an output transducer connected on the output side. So this is a summing junction here, to which some noise T2 gets added. Plus plus, that means these two signals here get added. We have a plus here and a minus from this side, so that these two get subtracted. The difference between the two signals is something called as an error, so this results in creation of an error. Now let us try to understand or examine this block diagram by an example. We'll use an example of antenna positioning system. So as to understand this block diagram. So for that I need to attach an image. Just a second, it will take me a second to attach that image. So let us try to understand step by step an antenna positioning system. Figure shows here an antenna positioning system. This is an antenna positioning system. So we want to, basically what we want is that we want to rotate this antenna by some angle. Say for example, we have this antenna, we want to rotate it by some angle theta. So what happens is that what we do is that we rotate this shaft as is shown here. So we have this as a, first of all, let's see what it is. We have a dish antenna, a huge dish antenna. Our aim is to rotate this antenna system by some predetermined angle or predefined angle. Say for example, in this case, we want to rotate this angle by some angle theta equal to 30 degrees. So what we do is that we move the shaft here by 30 degrees. The shaft is basically connected to a potentiometer. This potentiometer converts this rotation of 30 degrees into some voltage, and that voltage eventually reaches to the motor. This is a motor here, and the motor rotates this antenna system by the same angle. But if we look at it, it is very difficult to rotate this antenna system in this way. Why? Because the voltage that the potentiometer produces is very small or low. So what we do is that in order to rotate this huge antenna system, we use a power amplifier as is shown here. So we use an amplifier for amplifying the small voltage which is being produced by the potentiometer. This is a potentiometer here. So the voltage produced by the potentiometer gets amplified, and that amplified voltage is being given to a motor, and this motor rotates the system. There is a gear system. This gear system rotates, and the angle and the antenna rotates by that desired angle, say for example 30 degrees. So if we rotate this shaft by 30 degrees, the potentiometer produces some voltage. The voltage is being amplified by a power amplifier. That amplified voltage is being given to a motor, and the motor rotates the antenna by that desired angle. But the problem here, if we can see, is that say for example we intend to rotate the angle by 30 degrees and the antenna rotates only by 25 degrees. So we don't know, because there is no feedback. This is an open loop system. There is no feedback from the output to the input. So even if the antenna rotates only by 25 degrees, we don't know whether the antenna actually rotated by 30 degrees or not. So in order to avoid this thing, we are going to a closed loop system. This is a closed loop system, and this is what we are interested in understanding, and that's what I am going to discuss now. So this is a closed loop system. Now if we look at it, so the first thing that we see is that we have the same shaft, say for example we want to rotate the antenna by 30 degrees, so we move the shaft by angle theta it, which is 30 degrees. So this voltage, this tilt, basically this shaft changes the resistance of the potentiometer basically, so that potentiometer produces a voltage signal. So potentiometer produces a voltage signal corresponding to 30 degrees, and this voltage is being fed to a differential amplifier here. The differential amplifier here is nothing but a summing point or a summing junction. The output of this summing junction goes to some controller, say for example, and the controller rotates the motor by some makes the controller basically rotates the motor by the same angle, say for example by the same angle of 30 degrees. If we can look at this gear system, we see the motor shaft basically, let me use a different color, the motor shaft is basically connected to a gear. So this gear rotates by the same angle, and this gear rotates this gear by the same angle, so our antenna gets rotated eventually by 30 degrees. So let me erase it first. Now say for example we intend to rotate it by 30 degrees and the antenna rotates only by 25 degrees, or we intend to rotate it by 30 degrees but the antenna rotates by 35 degrees. So these are the two possibilities. The third possibility can be we intend to rotate the antenna by 30 degrees. So in all these three cases our input is 30 degrees. We intend to rotate the antenna by 30 degrees. So say for example, first case can be the antenna rotates only by 25 degrees. The second case is that the antenna can rotate by, say for example, by a larger angle, 35 degrees. And the third case is that the antenna actually rotates by 30 degrees. In the first case, what happens is that when we intend to rotate it by 30 degrees, it rotates only by 25 degrees. So we have a feedback system. If you can look here, we have a feedback, but we have a potentiometer on the output side as well. We have a potentiometer on the output side which is being connected to the summing point or the summing junction. So this is a feedback system. In the initial example, we had no feedback from output to the input. But yes, in this case, we have a feedback from output to the input. So what happens is that now, as I said, if the antenna rotates only by 25 degrees, this gear system also rotates by only 25 degrees. So this potentiometer basically produces a signal corresponding to 25 degrees rotation. The output potentiometer, there we have an output potentiometer, and this output potentiometer generates an electrical signal corresponding to only 25 degrees. So this is being fed back to the summing junction. At the summing junction, I can show you in a block diagram way. What I'm trying to explain is that say for example, I have this as a summing junction, I have input corresponding to 30 degrees, and I have an output which is only 25 degrees. So I have plus, I have minus. So the error, the difference of the two, which I said is the error, an error of 5 degrees gets generated, which is eventually being given to the controller. So the controller gets to know that yes, there is an error, and it has to process it, so that it has to move it. In other words, it has to move it by another 5 degrees. So it will send a message to the motor that the motor has to rotate by another 5 degrees. Now in the second case, so let us understand it by this block diagram. So all I mean is that we have an input signal, a summing junction, and then we have a controller. This is from the feedback path. This signal here comes from the feedback path, and this signal comes from the input transducer. Now the fact is that we are trying to rotate it by 30 degrees, and say for example the signal corresponding to 30 degrees is 3 volts, and on the other side when the output is only 25 degrees, so the antenna system is rotating only by 25 degrees, so this output shaft produces the output potentiometer, rather the output transducer produces a signal corresponding to 25 degrees, and let us say the signal corresponding to 25 degrees is 2.5 volts. So we are receiving a 2.5 volt signal on the other side which corresponds to 25 degrees, and a 3 volt signal from the input side which is corresponding to 30 degrees centigrade. So an error of 3 volts minus 2.5 volts means 0.5 volts is being generated. So this sends a message to the controller, rather the controller sends a message that yes, an error has been achieved, rather the desired output is not same as the reference input, as the desired output should have been 30 degrees which is only 25 degrees, and the reference input is 30 degrees. So this means there is an error of 5 degrees. So that's why the feedback tells us that yes, an error has been generated. So the controller works accordingly. It makes the motor to move again so that this error gets corrected. Now say for example we intend to move it by 30 degrees. The antenna system rotates exactly by 30 degrees. So in this case, corresponding to 30 degrees, the input transducer produces a 3 volt signal, and the output transducer again produces a 3 volt signal corresponding to 30 degrees. So in this case what happens is that in the input side we have a 3 volt to the summing junction. On the output side we again have a 3 volt signal. So the difference of the two is 0. When the controller receives a 0, it understands that the desired position has been achieved, and hence it stops working, that's the motor stops, and the final position of the antenna gets locked. So this is all about open and closed loop system. So in closed loop systems we understood that yes, if the desired output is not same as the reference input, then the control system takes corrective measures through the feedback so that it receives or it achieves the desired output. So that's all we have for the day. Now the last thing that I need to tell you is that I'll be sharing the notes with you students, with you guys, through the Google class. That is it.